Okay. Okay, good. So I think we're all set then. So Nicolò is going to tell us about Cobordism, K-theory, and tadpoles, part 2. Nicolò, when you want.
Okay, so first of all, thanks to the organizers for the invitation. It was really my pleasure to be part of this nice conference, and also thanks for the opportunity that they gave me for giving this talk online, and I'm very sorry that I cannot be there in person. So this talk is essentially a continuation of what Ralph talked about. I will be told is a nice introduction, and then I will actually go a bit more into the details of a recent paper we put out in August with Ralph, Christian, and Adriana. But in order for make the talk self-contained, let me also give shortly some more introduction and motivation. So I think this kind of investigation can be motivated from two different perspectives. The first question is a mathematical question, which is the question about the mathematical formulations of quantum gravity. And this is possibly, I would say, an open problem still. The second question is different qualitatively, and is the question about the signatures of quantum gravity in low energy effective field theory. So here is the question where probably the Swampland program has more direct impact. However, what I find nice, and what is actually the, if you want, the leitmotif for this talk, is that these two questions, in some cases, can be addressed at once. And this is actually what I find nice about these discussions about Cobordism. So this is a talk on symmetries in quantum gravity. So I would like to review first a few known facts. It's known that if you consider a d-dimensional theory of some manifold X, and if you have a symmetry, in particular, we'll consider higher, so-called higher forms global symmetry. So here I put the correct indices in order to have the current with index n. So to this symmetry, there is an associated current. And then you can say that when the symmetry is gauged, the current becomes exact. And when the symmetry is broken, the current is not closed in general because there are defects, so localized delta functions, which are breaking this conservation law. However, typically, when one is doing this kind of investigation, one is using cohomology or homology. So, for example, the current would naturally live in the cohomology groups of this manifold X. So it's a fair question from a mathematical side, and also then from a physical side, whether or not cohomology is the most generic language one can use, or if there are other languages, and in case there are, if they are relevant for physics. So this is the way I'd like to go to Cobordism, essentially. So Cobordism is an example of more general languages than standard homology or cohomology, and K-theory is another example. So there is a precise definition of these more general languages. You can also give an axiomatic definition, but I will not do that. Rather, I will try to stress what I think is one of the main differences. So standard homology groups or cohomology groups of the point have the property that they are zero, essentially. So they don't carry topological information. So if you use cohomology, here there is nothing interesting to be said in this case. However, for other more general theories, those which are called generalized cohomology theories, such Cobordism, this statement is not true in general. So the Cobordist groups of the point in general are non-vanishing. So they might be vanishing in some cases, but in general, they are not vanishing. And you can really track this fact from the very definition, since not every compact manifold is a boundary. So these groups are then carrying more information than standard cohomology or standard homology. So this topological information, and actually it's also physical. So the nice thing is that you can give a meaningful physical interpretation to these non-vanishing groups. Then to summarize briefly, what we have seen in the previous talk is that according to this nice proposal by McNamara and Waffa, there should exist some structure for these cobordism groups in such a way that the groups are vanishing, because these groups are detecting global symmetries. You don't want to have global symmetries in quantum gravity. This structure, this quantum gravity structure, is not known a priori. And we propose in this paper that there is a mathematical well-defined construction, which is known as Whitehead tower, which seems to lead closer to the quantum gravity structure, even though perhaps not really on the spot in some cases. So, but still, it seems to be an improvement. And then what Ralph talked about and what I will build upon is that when you gauge the symmetry, so whenever you have a non-vanishing group, you have a symmetry which must be either broken or gauged. I will talk about the case in which you gauge it. And then when you gauge the symmetry for some structures of the cobordism groups, in particular for spin and spin C, it seems natural to combine these groups with KO, so real K-theory and complex K-theory groups. This seems natural from a physical perspective, but it's also built on a very deep mathematical structure, which Ralph talked about. And then following this logic, what we showed in the paper in December is that one can really get very close to string theory information. So in particular to string theory tadpoles. So tadpoles are integrated Bianchi identities. The typical way you derive a Bianchi identity is starting from a Lagrange, and then you take equations of motion. However, what we propose is that you can perhaps be able to derive Bianchi identities without any Lagrangian information, just from a purely bottom-up approach, so by reasoning in terms of cancellation of Cobordism and K-theory charge. And then the last slide, in which I like to recap what Ralph said already. So as I was saying, a tadpole is an integrated Bianchi identity. So the Bianchi identity somehow is an object of this form. So the D of some field strength is equal to the current. And then the goal in these works we have been doing is to reconstruct the current without knowing the string theory Lagrangian. So without assuming any string theory Lagrangian effect. And as Ralph explained, we proposed essentially an algorithm to try and do this in certain cases. In the first step, you should add all the possible Cobordism invariants. So both Cobordism invariants are like characteristic classes which are capturing a piece of the Cobordism charge. And then you should add all of them because you want to capture all of the Cobordism charge. In particular, the map Ralph talked about, this Atiyah-Bott-Shapiro map, is just one invariant, but in general, you can have more than one. So add all of them, you construct linear combinations. And here, still the open problem, as Ralph was mentioning, is how to fix the coefficients of these linear combinations without really using string theory input. So this is something we are still thinking about. And for the moment, it's still an open problem for us. Then you construct a combination of Cobordism charges, but this might not be the end of the story because you can also have defects which enters in the current as localized delta functions. And then, of course, you can ask what are these defects, what is the organizing principle in which I can pick up a specific defect. Well, what we propose is that in the cases in which there is a map between Cobordism and K-theory, the defects which should enter the tadpole are precisely those which are pointed out by the map. So in particular, for spin C Cobordism, the defects will be classified by complex K-theory, while for spin Cobordism by real K-theory groups. So at the end, we end up with a tadpole, a generic form for a tadpole in terms just of Cobordism and K-theory contributions. And then in the paper with Ralph in December, we checked these in many examples, and it seems to work nicely in certain corners of string theory. So all of this essentially was already said nicely by Ralph. What I'm going to do is try to understand what happens when you generalize these constructions from Cobordism and K-theory groups of the point to groups of a generic manifold X. So the first thing one can notice already at purely mathematical level, so when you try to consider Cobordism groups of X and K-theory groups of X, well, you can typically write expressions of this time. So these are called the splitting lemmas or splitting properties of the groups. So essentially, the groups of X are given by the groups of the point, the one we talked about before and the one Ralph talked about, plus some remainder, which is really there because I'm fixing a manifold X together with its topology. So this is contributing to a topological charge. This reminder is known as the reduced Cobordism group or the reduced K-theory group. There are again precise mathematical definition, but I'm not going to give them. Just you can intuitively think of them as really those pieces of the groups which are sensitive to the fact that we fixed a manifold X. Then the question we asked in the paper in August is what is, if any, a physical interpretation of these most generic groups, possibly in terms of gauging this symmetry. So if it is possible to play a similar game as for the groups of the points, so combining Cobordism and K-theory, even in the case in which I have a manifold X and not just a point. So the first thing to do, of course, in order to answer this question is to compute these groups. So this is something we learned. We used a particular technique, which I'm going to discuss briefly. The next two slides are going to be a bit more technical. I think it's nice to see this shortly for a couple of minutes, but eventually we'll just state the result and then I will discuss the physical interpretation. So there are various tools to calculate these groups, and we choose one, which is probably among the simplest. And this tool is called a spectral sequence. In particular, we used what is called Atiyah-Izebu spectral sequence, which I'm going to introduce a bit more next. But the logic can be summarized intuitively in these three steps. So you start, so you want to calculate a generalized cohomology theory, which you don't know. You start from ordinary cohomology, so something you should know, or you have to know in order to follow this procedure. But this is just an approximation. Then you have to refine your approximation by means of maps, which are called differentials. Then once you are finished in using all of these differentials, so there is a precise mathematical way in which you are sure that you are finished, then the result you have, so what you can look at, is almost the final result. So it's almost your generalized cohomology, but for the cases in which there are torsional groups appearing. In those cases, you have to solve yet an additional problem, which is highly non-trivial in general. This is called what is called an extension problem. And typically, to solve this problem, you need extra information, which the spectral sequence cannot really provide, at least for the Atiyah-Izebu spectral sequence. So let me now enter a bit more the details just for a couple of slides. A spectral sequence, more precisely, is a collection of pages and differentials. So pages, you can think of pages of degree R with entries P and Q as some sort of grid or a lattice with entries. And of course, at the first levels, these entries will be our homology group, so the starting point. And these differentials are the maps I was mentioning before in order to refine the approximation. And then the rule is that the next page, the R+1 page, is just the homology or the cohomology of the previous page with respect to the differential. So what you have to do, essentially, you have to turn the pages, go from one page to the other, so improve your approximation by using these differentials. And eventually you get closer to the result, which I'm calling G's for generalized cohomology or homology. And then there are these two problems I was mentioning. First of all, the explicit form of the differentials of this map is not known in general. It is known for certain cases and for low degree, but in general, these are highly non-trivial mathematical problems. So this is already a place in which you might not be able to continue with your calculation. Then, even if you might be able to finish with all of the differentials, the final result, which you can read in the last page, which I'm calling infinity page, is the last page after once I'm done with all of the differential. To read the generalized cohomology or homology, you have to sum over the diagonals of this page. But again, this is true up to extensions, and I will give you an example now. Just to be precise, what I call the Atiyah-Izebu spectral sequence is a precise mathematical thing, a precise mathematical algorithm which works when you have a fibration of this kind and you know the generalized cohomology or homology associated to the fiber. Then there is a theorem which is telling you that you can start from the second page, which is given by these homology groups or cohomology groups. And then this is converging after a finite number of steps to the generalized homology theory up to extensions. So to give you an example, which is not really realistic for the calculation we've done, but just to understand, this is how some very simple second page can look like. So there are many zeros. So there is a grid with Q and P indices. And there are many zeros. The more zeros you have, the easier the problem. But there are also non-zeros entries. So these are the first approximation, my ordinary homology or cohomology. Then you act with differentials. Differentials are maps which are connecting from one entity to the other. In particular, you have to count correctly the indices. And in this case, at the second page, the only map is the one I'm showing here. There are no other maps for degree reasons. Then you have to understand how this map acts. So what is the effect on this entry? And okay, let's assume for the sake of simplicity that the effect of this map is that it kills completely this entry. So we end up in the next page, the third page, with this structure here. Now you have to act with the third differential, and you can show by doing again a very simple counting of indices that there is no way in which a third differential can act in this situation, because the differential will either start from a 0 or end up to a 0 entry. So there is no way in which this differential can act non-trivially. So this is the precise mathematical meaning in which you are finished with the differentials. And then you can try to read the result. To read the result, you have to do as follows. So you look at the diagonals in this direction. And then the 0 level of your generalized cohomology theory is essentially just this entry, is the only element of the diagonal. The first level, there are 2 entries, but they are both vanishing. So in this case, this is trivial. In the third case is non-trivial. Let me call these groups B and A generically. And then to read from here the final result, you have to solve what is called this extension problem, which means that you have to put G2, which would be the extension of this group by this group, you have to put it into some sort of short exact sequence in this way. But then this does not imply that G2 is just the sum of the two, because this depends on what A and B are. So you have to tell me first what A and B are, and then I can tell you probably if this is just a sum or something else. Actually, even if you tell me, there are cases in which I cannot still tell what this is. So just to give you an example, and then I'm done. Let's say, take A and B to be Z2. Well, then it is known that this short exact sequence can give either Z2 plus Z2 or Z4, but the spectral sequence is not telling you which one you have to choose. So this you have to use some other to understand this. Now, this was a bit mathematical, but there is also physical information inside the spectral sequence, and this slide is an example. So it's known that type 2 branes must wrap a spin-sim manifold, otherwise there is an anomaly. This is called a Friedwitten anomaly. And somehow this information is encoded into the spectral sequence if you use it for K-theory. And how this happens is by the fact that the third differential in the spectral sequence for K-theory is actually proportional to what is called the third integer stiffening within a class. So vanishing of the third differential actually means vanishing of the third integer stiffening within a class, which is precisely the definition of spin-sim manifold. So for some reasons, the spectral sequence knows about Friedwitten anomalies in this particular case of K-theory. Okay, so this is the tool we used, which has some nice also physical properties. And we use it for very simple cases because we just started to learn how to use this tool essentially. So we started from spheres, then tori, and then we look at K3 and Calabi-Yau3. So what I'm going to tell you is just for these manifolds, and I don't mean to be general. So for these kind of manifolds, what we showed is that the K-theory groups and the Cobordism groups of X can be written as a sum over the groups of the point with coefficient the Betti number of X. So fixing X is somehow detected by the fact that there are the Betti number of X appearing on the right-hand side of these sums. And then what we wanted to understand is what is the physical interpretation of this. So we know the physical interpretation of the groups of the point, thanks to Marian Waffa. And then what we proposed is that the physical interpretation in these cases of this group of X is that they reproduce the pattern of global symmetries which arise from the dimensional reduction of the theory on the manifold X. So I'm not anymore like in 10-dimensional, 11-dimensional, but I'm compactifying the theory on X. For example, I can compactify in Calabi-Austrian theory.
Nicolò, sorry to interrupt you for a
Yes.
moment. It's 5 minutes to the end of the talk now.
Yes. Okay, I will speed up. Okay. So this essentially the message of the paper. To give you a bit more detail, if you look at the K-theory groups, they classify, you can understand that these groups classify n plus m branes, which are wrapping k minus m cycles of X. And this consisted with expectation from dimensional reduction. And actually, if a brane survived, it means that it's actually anomaly free because it survived the spectral sequence in which the fluid with an anomaly cancellation condition is implemented. And we have similar results also for real gating. Now, for cobordism, the interpretation is similar, but there is a subtlety which is going to take me the last part of this talk. So for cobordism, again, we have a sum over the groups of the point with coefficient and Betti numbers. But we have to distinguish, we have to look at this index, and we have to make a distinction to give a physical interpretation. So the index of a cobordist group must be positive because this is the dimension of the manifolds in the cobordist class, so it has to be positive. However, we are splitting the index as n plus k, where k is the dimension of X. So it can be that n is negative, but still in such a way that n plus k is positive. And we have really to distinguish among these two cases. So when n is positive, we can really play the same logic that Ralph discussed already. So there is really a one-to-one correspondence between cobordist groups of the point and K-theory groups of the point on the right-hand side in these sums. So for each cobordist group, there is a K-theory group associated, and then we can construct a tuple by combining them. However, when I'm in the other situation, in which n plus k is positive, but n is not positive, then there is not always a K-theory group which is analogous to the cobordist group. So in this case, it can happen that they are not really paired one-to-one, and this is where our interpretation is perhaps a bit more speculative. So let me give you an example of these cases. So in the paper, we looked at few examples. Here is one. You can compute K6 of K3 and omega 6, of Calabi-3 and omega 6 of Calabi-3. And then these are sums over the groups of the point with coefficient and Betti numbers. What you have to do in order to extract the information about the gauging of this symmetry is that you can combine the groups. Here I'm pairing with the same color. So this will give you tadpoles in a 4-dimensional theory because I'm compactifying on Calabi-Yau. And actually they give you a number of tadpoles. So B6 tadpole from the first terms, B4 tadpoles from the second terms, and so on. And these are tadpoles for 3-form symmetries in the compact theory. But also from this structure, we can understand what is the origin in the non-compact theories, in the higher dimensional theory. They originate from 9, 7, 5, and 3-form symmetries, because you have to read this index essentially, from the higher dimensional theory. So here, somehow, in these expressions, it is encoded all of the information of what I see in the 4-dimensional theory and what is the origin from the 10-dimensional theory. Now, last thing before concluding, I was saying that we have also attempted an interpretation for the other case in which n is negative, but still this is much more speculative than the rest. And what I'm going to say is just, we did it just for the case of Calabi-Yau, while the other situation for n, we did it also for the other manifolds. So we have to give an interpretation in this range of indices. We have to distinguish when the index is odd or even. When the index is odd, we propose that actually the cobordism symmetry is broken because there is no appropriate gauge field in the theory to gauge it. So we think that it's highly possible that in this case the symmetry is broken, so you cannot combine it with K-theory and reconstruct a tuple. It's a different case. However, when n is even, there is in principle a way to play a similar trick. And what we propose is that when it's even and is less than 6, because X is Calabi-Yau in this case, these groups omega 0, omega 2, omega 4 will contribute to tadpoles of the omega 6 case. And actually, we can do this a bit systematically. So we built up a table with all the possible contributions. So the first line of this table is the example I explained to you explicitly with these 4 terms. Then these groups are those for which the interpretation is less clear, as I was saying, but since the index is even, we propose that, for example, this group is a sum over these 3 terms, and it's natural to say that this term will contribute to the same tadpole as this, because there is a C8 gauge field involved in both cases. And in string theory, actually a contribution of this kind seems to arise from a localized O7 plane. You can
Nicolò,
also play
question time now.
Yes, okay, so you can also play, I'm finished. You can also play the same game for all the other terms, and they all work, but for these 2 terms, we don't know a string theory corresponding interpretation. So either for some reason these other terms accidentally work, or if this table has to work in general, then also this term should have a string theory interpretation. So this is a possible way to propose new contributions in tadpoles from which are there in string theory. So to conclude, the absence of global symmetry seems a fact in quantum gravity, and it seems to be true also when we enlarge the notion of symmetry, and this statement has predictive power. And this talk was about the generalization from cobordism groups of the point to cobordism groups of X. And open questions are many. So first of all, we should look at more complicated groups. We just really look at the simplest examples possible. And I think it will be very interesting to clarify what Ralph said. So the origin of this tadpole from bottom up, in particular, if we are able to give a first principle derivation of those coefficients, we might even be able to give a support to the string campus principle. And then, as Ralph was mentioning, it's possible that there is this possibility that Cobordism and K-theory are hinting a new object in string theory, but of course we need an independent way to confirm or disprove this prediction before claiming that there is really a new object in string theory and quantum gravity. Thank you for your attention.
Okay, questions for Nicolò? Check.
Hi, yeah, thank you for the nice talk. So in both this talk and the last one, you mentioned the idea that the terms appearing in tadpole cancellation would be Cobordism invariance as a conjecture. But I think you can actually see this directly. So if you had some term appearing in a tadpole cancellation that was not corresponding to a Cobordism invariant, the reason it wouldn't correspond is because it would vanish on any closed manifold. And so you could put that term in your tadpole cancellation, but it would never contribute. So I think you can see directly that the terms in the tadpole cancellation will always be Cobordism invariant.
Sorry, can you repeat it, because the audio was off? You can see it?
Yeah, sorry.
The fact that it vanishes on what?
So as you discussed, the space of Cobordism invariance is not all characteristic classes. It's only the characteristic classes that are non-zero on some closed manifold. But this is sort of a quotient structure. And so the other characteristic classes, the reason they don't give Cobordism invariance is because if you evaluate them on any closed manifold, they give 0. And so even if you put them in the tadpole cancellation, they wouldn't.
So I can include them, but they are just trivial, you're saying. This one.
Exactly.
Okay, yes.
It's a quotient, not a sub.
Okay, yes, thank you. It's nice, thanks.
Any further questions for Nicolò? Well, if not, I have a quick one myself. So you were telling us about the Cobordism groups of manifolds, and you were using them to study dimensional reduction on different fields from the Cobordism perspective on a manifold X. But if you had asked me this question, I would have guessed that the Cobordism group that would have been relevant for that, if I'm interested in, for some reason, in fixing part of the topology to be the manifold X, I would have guessed is omega of X times whatever, and then I let the whatever fluctuate. How is it? Because the Cobordism that you look at is Cobordism groups of manifolds with maps to X. So are the two related, or Cobordism groups of manifolds with a maps of X versus Cobordism groups of X times M, where I allow M?
I'm in this, I'm not sure I understand. I'm in this situation where I'm mapping the manifold to X, right? And I'm fixing X. So what this is capturing is essentially, I mean, this map is not, so for example, a cycle in M can be non-trivially mapped to a cycle in X only if there is a non-trivial cycle in X. At least this was my understanding, let's say. So I'm discussing these cases.
Okay. Are there any further questions for Nicolò? Well, if not, then thanks a lot again.
Thank you.